Okay, so let's talk about how an IR actually works. So at the heart, every single IR, well, back it up a minute. So we always talk about Fourier Transform infrared spectroscopy, or FTIR. And actually the FT has become so common at this point it's almost dropped now. We just call it infrared spectroscopy. So it's kind of like NMR. NMR used to be FT-NMR. FT-NMR is basically what everyone does these days, so we just get rid of the FT and we just call it NMR now. How does it work? So inside our IR we have a light source, and this is going to create a broad spectrum of frequencies of infrared light at different intensities. And we want to focus these down to the wavelength that we're actually interested in. So what we're going to do is we're going to take our light source and we're going to project it to a semi-transparent, semi-reflective mirror. And two things are going to happen. One, part of our beam is going to go up and then bounce back down. It's going to hit the stationary mirror. The second is going to go to a second mirror that's moving. It's moving as a function of time. So it's going to go back and forth. And this beam's going to hit it, come back, and at this mirror, they're going to recombine. Now, the thing about the light waves, the infrared rays, is that they have their own frequencies and their own phase angles. So the nice thing about sine waves is unless their frequencies are super close and their phase angles are just about right, you're going to get destructive interference. So this moving mirror creates a specific frequency that is the only frequency that is constructively interfered with the other light coming off the stationary mirror. And this is what's referred to as a Michaelson Interferometer. So what this is going to do is this is basically how we're going to make a monochromatic IR light source. Based on its position relative to the stationary mirror, we're only going to get a certain frequency that passes through. Now, this frequency is going to get passed down. If we want to be quantitative and when we need this to do IR, what we're going to do is we're going to pass it through a beam splitter. And what the beam splitter is going to do is going to split the signal into two equal parts. The first part is going to get reflected around and go to our reference detector I0. The second beam is going to go through our sample and hit our second detector I1. Our transmission here is defined as I1 over I0. And the reason we need to do this is the light bulb doesn't necessarily produce the same intensity signal for all frequencies of light. For some it may be better than others. So this normalizing to this reference frequency basically tells us the transmission regardless of the strength of the light passing through it at the time. Now, you see time here, what you don't see here is wavelength. So what we record in terms of raw data is transmission versus time. The Fourier Transform, that FT here, is what's going to convert us from time to wavelength because we know the position of this mirror is a function of frequency, or is a function of time. And our Fourier Transform converts us from the time domain to the frequency domain. So here, this is where we get the switch from time versus transmission versus time to transmission versus wavelength. So that FT there is what's converting us from a traversing mirror as going back and forth as a function of time to the actual wavelengths we're interested in. So this is the gist of how an IR works. What do we actually do with the data? Well, sorry about that. We'll talk about that in the next video.